This is the midterm demo for the autofocusing and color identifying lenses for mild visual impairments. The team consists of Julie Gallagher, an electrical engineer, Renato Morales Jr., a photonic science engineer, Midhut Satanov, a photonic science engineer, and Kayla Stanley, a computer engineer.
We'll begin by delving into the parts and subsystem overview.
Main PCB. Our main PCB houses our ESP32 and our 5-volt regulator. We had a difficulty with our USB connection as it was a female type A and we needed a male type A. We were able to fix this by just bending the USB port upwards to an angle and then fitting in a male-to-male adapter. As for a regulator, it was intended to be placed as shown on the picture on the top of the board. But our connections were flipped during the PCB layout, and we had to solder our pins underneath the PCB, and our regulator is, instead of being on the top, is placed underneath the board. We will fix this during our second iteration of our regulator board. For our 5-volt regulator board, we have a very big issue. Our jack connector is wired incorrectly. Therefore, if we were to connect our battery, it will fry our component. Therefore, we had to solder in wires to connect to a power supply as a temporary solution, as shown in the picture. But we will reorder a second iteration of this board.
Our autofocusing system relies on interfacing our Raspberry Pi with the camera module and using a Sobel filter algorithm to determine whether the image shown in the lens is in focus. Based on this data, the Pi instructs the motor to adjust the furthest lens until the image is in focus. This represents one half of the focusing system, as this information is then sent to the primary lenses, which will be discussed further on.
Color detection board. The color detection board relies on the TCS3200 detecting light that is reflected off a surface being illuminated by our 4 LEDs. This incoming light is then absorbed by the photodiodes on the TCS32000, and with these RGB values being sent to the ESP, it can interpret it using a least square method and determining what color the object is. As for the board, it is working well, as later on we will show the test results, but we will be ordering a second iteration since the first one doesn't allow us to control when the LEDs are turned on and off.
The second half of the color detection system uses the same components from the autofocusing system, relying on the camera module V2 to capture an image, running a program, and then determining the color of the object that is in focus. This information is then sent to the Raspberry Pi, which then gives us the output color.
Our primary lenses sit in line with the optical axes of the user's eyes. Once the autofocusing system successfully finds focus using the lenses placed in line with the CMOS sensor, the change in position of that lens is used to instruct the primary lens system's movement. Due to an unresolved coding error, we have chosen to use the ultrasonic time-of-flight sensor to determine the movement distance for this demonstration. The time-of-flight sensor interprets the distance between the lenses and the object they are attempting to focus on, and then sends this information to the ESP32. Then, based on predetermined optical equations, the lenses are moved by the motors to adjust to the desired optical power.
We'll go through a couple scenarios in which our product would be able to assist those with minor visual impairments. Starting off, let's consider an individual with achromatopsia. So in this scenario, we can see that this individual has achromatopsia, meaning that they don't perceive color at all. And so while we can see that in the original image we have red and green here on the screen, let's go ahead and perceive the world as they would and see whether or not the filter works. All right? And so we can see that the colorimeter now scans the red and the green paper and displays that information on the screen. And in the final product, an audio system is going to deliver that information to them. Now let's move on to scenario 2. So here we're observing an individual with hyperopia, meaning that it's difficult for them to focus their eyes on something close, otherwise known as farsightedness. And so in this demonstration, we can see how our primary lens system uses the time-of-flight sensor to detect the distance between itself and the lenses, and then moves those lenses accordingly through the ESP32 and our motor system. And we know that it's working properly because the spot size of the laser beam that we're shining through the lenses is decreasing as the lenses move. And this is going to be demonstrated further when we go into specifications. Now we'll go into our specifications. The parameters that we were testing for were to ensure that the color accuracy of both color systems were at least 80%, that our focusing power could be variable between negative 1.5 diopters to positive 2.5 diopters, and that the time to focus did not exceed 1 minute. So here we're again demonstrating the colorimeter by showing it on 3 different shades, red, green, and blue. When we hover over them using the colorimeter, you can see that on the right side of the screen, the same exact RGB values and the corresponding colors are shown. Now the second half of the color detection program uses a similar principle, but through the use of the camera module V2 and the Raspberry Pi. And so we can see here a demonstration of that system, where we're shining the camera onto 3 separate colors, again, red, green, and blue, and then receiving that information on the screen. Our color detection tests showed that both systems were completely accurate 100% of the time. However, this should be taken with some caveats. We do need to calibrate the colorimeter and the camera module V2 when we initially perform this test, and so we're going to need to continuously adapt it to new light conditions whenever we use the product. This is something that we hope to integrate a little bit more seamlessly into the final product, because currently our calibration is an external feature that we need to set up each and every single time. Additionally, we want to program more colors so that it isn't just red, green, and blue that we're detecting. We were able to consistently and reliably provide between negative 1.5 to positive 1.5 diopters and adjust our lenses to be able to accomplish this. And you can see several examples of it here in this video. And the main issue that we were beginning to run into was that every once in a while our motors would become jammed, as you're about to see in an upcoming clip. Besides that though, we wanted to ensure that the laser beam width of the laser that we were shining through the lenses became smaller as we focused the lenses, and this appeared to be the case consistently.
For this demonstration, the time-of-flight sensor consistently determined a distance within 5% of the actual distance. By testing a laser beam through the system, we can determine the focal length. The beam width had a starting beam width of 1.5 mm and a beam width of 3 mm when traveling through both lenses, set to 0 diopters of optical power. This is consistent with the magnification of 2 that we anticipated from the individual focal lengths of each lens. By measuring the beam width before and after the lens's attempt to focus, we can see that the system consistently brought the laser beam into focus. Our main concern here is with the threaded rods used as rails and our motors. More calibration is required to ensure both motors are rotating at the same speed. In addition to this, the threaded rods tend to jam at times, which interrupts the distance of movement. New threaded rods will be tested to see if the jamming can be reduced or prevented altogether, as it is essential that the lenses move to the correct position consistently. With the issues aside, the primary lenses move to their position in approximately 8 seconds.
Now, for our last demonstration, we want to show off the autofocusing system. As of the current moment, we are having difficulties with this subsystem, and some of them will be on display here. I'm going to show 2 successful attempts from our autofocusing. In this one, you can see that it requires a little bit of time before the lenses move into place, and the Raspberry Pi records this as a success. And in the second attempt, similar progress is made. However, in this second attempt, we already begin to see some issues. Here, we can see that the system does not conclude and say definitively whether or not it is in focus. It's something that we're going to need to address. And then finally, we do want to show off the fact that if the system is already in focus, then it will not move. And that can be shown clearly here. Before we move on to the discussion of the results of our test, we want to show the images that we acquired from those 3 examples. And so here we can see that when looking through the lens, the image is in focus.
Our autofocusing system still requires fine-tuning before it reproduces results reliably. We've only tested one set distance, and as of now, if focus isn't achieved quickly, it isn't achieved at all due to delays in the motors with the ESP32 communication. This means we don't have a reliable upper limit time approximation at the moment, but focus can be achieved as fast as 5 seconds. This also only includes half the system, as this doesn't include the time it takes to send the information to the primary lenses and for those lenses to move. We plan on fixing this issue with more testing and further code adjustments.
For our final specification table, we can see that our color accuracy was actually exceeded, and that 100% of the time we did manage to reach our goal. However, this should be taken with a couple of caveats. We did only program it to be able to detect 3 colors, red, green, and blue. We need to include a wider array of colors in order to be able to detect them. And then also, besides that, we need to prepare for different lighting conditions by calibrating our instruments correctly and making sure that we can pre-calibrate them under different and changing light circumstances. As for focusing power, we reached between negative 1.5 diopters to positive 2.4 diopters, which is well within the requirement that we are going for, but our system actually can handle more, and we hope to demonstrate this in the final demo. As for the time to focus, we are aiming for less than 1 minute, and our actual is roughly 20 seconds. This combines both the amount of time that it takes for the autofocusing and also for the primary lenses to move.
Thank you for watching our midterm demo. Team P.A.U.L appreciates your attention.